and today we are going to talk about the expectation values of dynamical quantities. When we talk about the dynamical quantities, it can be your position, momentum, kinetic energy, and when we talk about expectation value, we are simply talking about the average value. So we are talking about the average value, your average position, your average momentum, or your average energy. Now, if X is your position operator and P is your momentum operator and E is your energy operator, then the expectation value of your position is denoted by this symbol, and the formula is given by psi star and X operator psi d of X. Similarly, for momentum, minus infinity to infinity, psi star B d of X, and for energy, so let us see the formula in detail. Now, the average expectation value of position, it is denoted by this one, and the formula is given by this one. So this equation 1 is for the normalized function psi. If the function psi is normalized, then it is the expectation value is given by equation 1. But if the function psi is not normalized, then the expectation value of position is given by this equation number 2. Similarly, the general form of the expectation value is denoted by, let's say A. Let A be any operator. Then in that case, the expectation value of this operator A is given by this equation, similar to equation 2. Okay, in this case, the operator is position, but here it is the general operator. It can be any operator. But if we know that this function psi is normalized, then the denominator term will not be there. So in that case, your expectation of A is given by this equation, and this equation is for the normalized wave function psi. Now, the expectation value of momentum B of X, we are considering B of X, so we are considering the momentum only in the x-axis. So in that case, it becomes B of X, and here instead of R, because R is a three-dimensional space, but we are considering only along the x-axis, so it will be replaced by X, here also X, and here D of X. But we already know that the momentum operator is Hi del of del X from your last quantum class in your last semester. And in the last semester, you might have learned about B operator B as Hi of this del. But since we are considering only one axis, that is x-axis, we don't need this del because this is a space operator, three-dimensional operator. So we are considering only one axis, that is x-axis. So in that case, we can write here partial derivative of del of X. So we can put this value instead of operator B here. So this value will give you the expectation value of your momentum along the x-axis. Similarly, if we try to do it for the kinetic energy, see, everything will be same, just that you will put here kinetic operator, energy operator, and we already know the kinetic energy operator in your last quantum semester, and here it is represented by minus h squared 2m del squared del of x squared. So what happens is that this minus h squared 2m as a constant, it can come out from the integration, so you are left with this term, and this is a double integral, so you can write in this way. Now, using the partial integration formula uv, you can further simplify this integration into the below integration. All right, so what happened here is this psi star, it becomes 0 when x tends to plus or minus infinity. So in that case, this first term will become 0, so you are only left with the second term. Minus will get plus, and you are left with this term. All right, and this two term we can further write in this way: square root of the modulus of del psi del of x dx. So this value will give us the expectation value of the kinetic energy. Similarly, for the energy Em of an eigenstate psi n RT, the expectation value of energy is given by this one, and this is the formula. All right, now since this energy operator is given by IH del of del D, so it is a partial differential of time. So in that case, we want to further simplify the function psi n, because psi n is a function of space and time. So we want to further simplify this function. So here psi n r just represent the wave function belonging to the space, and this term represent the wave function contributing to time. All right, it's contributed by the time. So in that case, we can replace, instead of psi n, we can replace this function by this equation. Okay, by this equation. So let's try to substitute that. Okay, and one more thing, there's a mistake here. For the complex conjugate psi n star, here it should be plus, because the complex conjugate of this one, this will become plus. All right, so you have to make these changes. All right, so what happened is that, see, I of ih is constant. It can come out from the integration, and if you partially differentiate this term with respect to time, this term is a constant, and this term, the exponential term, will stay as it is. And if you differentiate the power, then you are going to get minus I en of h. So h and h will get cancelled. I and I will be I square, which is minus 1. So it will get cancelled with this minus. En is a constant, it can come out. And this is e power plus, e power minus. So this two terms will get cancelled. So we will be left with psi n star r, psi n r d down. Alright. Now, this term looks like the total probability equation. Now, we know that if the function psi is normalized, then this total probability is equal to 1. So if the function is normalized, then the total probability is equal to 1. So once we put the value of this integration term as 1 in the above equation, then we are going to get the expected energy is equal to En. Alright, so this expected energy is constant with respect to time.